So when we talk about decarbonising the energy system, we're talking about decarbonising all. And the question is, how do we do that, and what's the most cost-effective way to do that? And we need to think about the technologies that deliver that. And today we'll talk about the role of electrochemical technology, the role of making hydrogen, and the role of hydrogen in decarbonising, for example, some of this liquid fuel demand, and perhaps a significant fraction of this gas demand, the role of energy storage, particularly for system balancing between the different demands for power on a second-by-second, day-by-day, week-by-week basis, and the potential for fuel cells to be used as very high-efficiency energy conversion devices, both for transport, for example, in this to displace some of these liquid fuels, but also for power generation. I think the other thing we also have to remember in terms of the driver here is, whilst we focus on carbon and the low carbon transition is a key driver, actually air quality is a probably even more pressing driver, certainly in some parts of the world. This is slightly old data, and I also suspect today in a pandemic it might look a bit different. But this is a NOx map of London, and the bright red colours indicate the higher NOx concentrations. And it shows that they follow the main arterial roads around the capital city, and this is Heathrow out here. So it's coupled to transport demand, and it's particularly coupled to fossil fuel powered transport demand. So air quality is a driver in many cities in the world, and it's another fact we need to think about in terms of the motivation for looking at some of these cleaner, non-combustion based technologies, because a lot of the NOx emissions come from the combustion process. I am going to talk a fair amount about hydrogen. And when we talk about electrochemical technologies, we're going to talk about making hydrogen, and we're going to talk about fuel cells for converting hydrogen. And the concept of hydrogen and its role in the energy transition is actually extremely topical at the moment. It's extremely topical at the moment. Hydrogen has had previous waves of enthusiasm back to the 60s when people first sort of turned the concept of a hydrogen, through to the 90s and 2000s when there was a lot of surge of interest in hydrogen cars in particular. But I think today we have formed a nuanced and balanced view of hydrogen, which is that look at decarbonising the whole of the economy. There are some sectors of the economy, for example, long-distance transport or industrial heat, which are actually quite difficult to do with just using low-carbon electricity. And this is where the potential for a low-carbon energy carrier in a molecular form, like hydrogen, starts to become of interest. So I think we're living in a more nuanced world and a more informed world in which we think about the interplay between low-carbon electrons, for example, from wind and solar, of course, using those directly where we can. And it's always a good idea to use that electricity directly where we can. But for those applications where that perhaps is difficult to provide the functionality we need, for example, electric aircraft have quite short range, or long distance trucks running on batteries today still have relatively limited range. Or as I say, for some industrial heating applications, or for industrial applications like steel making, here it may well make sense to take those electrons and turn them into hydrogen through an electrolyzer, and then utilize that hydrogen in the built environment, the transport sector or in the industrial sector. So it's the interplay of electrons and molecules that is, I think, the key to achieving the lowest overall cost of decarbonisation going forward. And there's a big debate about the relative balance of those things, but I think it's very clear to me that you need both if we're going to cost effectively decarbonise. So let me start by talking about hydrogen from electrolysis, and electrolysers are, of course, an electrochemical technology, the subject of today's discussion. And when we look at green hydrogen from electrolysis, there are effectively three solutions that we have available to us, two of which are commercially mature today, and one of which is not yet commercially mature to the same scale, but is a subject, I think, of interest. And indeed, as it was mentioned in the introduction, this is some work we're going to be doing through the bp-ICAM program for the next 12 months, and I'll talk a little bit about that. For anyone who follows this, you'll have seen a surge of interest and national commitments to green hydrogen from many countries around the world, including in Europe, but also in China and Australia, and even the UK coming forward with some statements very shortly around its ambitions around hydrogen. So when people talk about green hydrogen, they're really talking about taking electricity and directly splitting water to make hydrogen and oxygen. And it's the hydrogen that we particularly want. We have today available electrolysers. These have been available for over 100 years. They're commercially much. You can buy an 100 megawatt electrolyser and use that. It's a relatively low temperature technology, and it's the lowest cost route to green hydrogen today. We also need to remember that today green hydrogen is the most expensive form of hydrogen. So we'll look in a moment about where costs may be going. In terms of green hydrogen, alkaline is the cheapest available option today, reflecting the maturity of the technology. But it has some disadvantages. It doesn't particularly load follow well. So if you coupled it to a variable renewable power source, it doesn't particularly manage that well. And it can't produce hydrogen at pressure. And it has a relatively high footprint, so it needs quite a lot of space. PEM electrolysers are relatively, in the context of this, new player. They are commercially available. They're of increasing interest to a number of organizations. And a lot of electrolysers now will sell you both an alkaline or a PEM electrolyser. PEM electrolysers are more compact. They can produce hydrogen at pressure. They're much more flexible and can load follow or demand follow much better than an alkaline electrolyser. They do, however, contain quite a lot of expensive materials, and in particular noble metals of platinum and iridium, which do provide some concerns about supply chain for the widespread adoption of these technologies. But and I'll show you a photograph of our hydrogen fuel cell car at Imperial College shortly, but if you go to a Shell forecourt, if I can say that on this call, and fill up your hydrogen car with hydrogen, for example, in one of the forecourts on the M40 or on the M25, that is a PEM electrolyser manufactured by a British company called RFC Power based out of Sheffield. So both of those technologies are here today and improving all the time. My particular interest and interests of other colleagues, both at Imperial College and elsewhere in the UK, is also around solid oxide electrolysis. This is a high temperature electrolyser, effectively putting in steam and transporting the oxygen ion off that steam and producing hydrogen. So it pulls the oxygen off, produces oxygen and hydrogen. So in this case, this is a high temperature device. It runs at elevated temperatures, and we'll talk a little more about it in a minute. But it has the advantage of much higher electrical efficiency compared to the low temperature technologies. And that's its main asset. It can also take in CO2 as well as H2O, and you can electrolyze oxide to carbon monoxide or as steam and CO2 to syngas. And so that's actual interest, of course, for integration into other industrial processes or for chemicals production. So where are the costs today? And anyone interested in looking at this space, I commend this report from IRENA on green hydrogen cost reduction. It came out late last year. It's a good introductory overview of where these technologies sit today. This is their data. I've had nothing to do with the report, but it gives you some estimates of hydrogen production costs in US dollars per kilogram of hydrogen, being around $5 US today, but there's a range. And it makes some projections about where costs may get to, and they're projecting out to perhaps $1 per kilogram of hydrogen out into the future if everything aligns. If we look at the cost of green hydrogen today, 60 to 80% of the cost of that hydrogen is the cost of the electricity that's going into the electrolyzer. So future costs of green hydrogen are very sensitive to the renewable energy price. And this cost down curve here makes some estimates of the relative importance, for example, of reducing electrolyzer cost. This big drop down here is based off the decrease in renewable electricity price. something around electrolyzer efficiency, which of course is also very important because it impacts the amount of electricity you need, something around capacity factor, lifetime, and risk, which is related to the weighted average cost of capital. So if all of these things align, the authors of this report are projecting that we can see $1 per kilogram of hydrogen. Of course, whether we'll get there remains to be seen, but it shows the potential and certainly getting a lot of people excited about the opportunity. As I say, my particular interest and interests of some other colleagues is in high temperature electrolysis. And this is a couple of graphs to try and explain why we're interested in high temperature electrolysis. This is about energy consumption, kilowatt hours per cubic meter of hydrogen. For a liquid phase process like the low temperature electrolyzers, or a high temperature process like the solid oxide electrolyzers. This change in energy here reflects the heat of vaporization of water. So in this phase, we're dealing entirely with steam. We're not having to go from a liquid to gas transition, and that saves us some energy. But you can also see that this is the Gibbs energy for splitting water. So this is the amount of energy we need to put into an electrical reactor as the theoretical minimum to split water. This is the enthalpy of that reaction. And while the enthalpy stays relatively independently of temperature, the Gibbs energy comes down. So that means we need to put less electrical work in to split water to make hydrogen as the temperature goes up. Of course, we still need to put the same amount of total energy in, and so we can balance that decreased electrical energy demand by putting in heat. So it allows us to put in both heat and power to produce hydrogen. And so if we can co-locate our electrolyzer with sources of heat, for example, alongside other industrial processes, it provides us with much lower electrical energy demand. And of course, the electrical energy is the expensive bit normally of the overall process. This is shown a little bit differently on this plot below, which shows us the voltage against current plots for high temperature electrolyzer, at least schematically. All electrochemical reactors have this relationship where current is reaction rate and voltage is essentially energy or thermodynamic driving force. Here we have in fuel cell mode, so as we draw power, and in other words, we draw current from the device, the voltage falls. Here we have in electrolyzer mode, where as we inject current to make hydrogen, our voltage requirement goes up. Now, you can see that in this mode of an electrolyzer, down here, the reaction is endothermic, and in fuel cells are always exothermic. But we need to put heat in, and we can indeed operate our electrolyzer at such a point, so-called thermoneutral point, which at 800 degrees C is about 1.29 volts. If we operate our electrolyzer at that point, the heat that the ejected into the system by the overvoltage, in other words, the overpotentials in the system, actually balances the heat we need from the enthalpy of the reaction. And so we have an electrolyzer that is extremely efficient, approaching 100% efficiency for electrical work, and has no temperature gradients, which gives it lifetime benefits. And this is why, on paper, this technology is very interesting. It can readily get over 90% electrical efficiency. And if you don't count the value of the heat, you can get 100% electrical efficiency in endothermic mode. So this, just very briefly, approach we've been taking within my own group, and we're very interested in the electrodes that are made and how you design electrodes that allow the both stable in the operating conditions, particularly sufficiently active. And this is the sort of approach we're going to be taking forward in part in our new bp-ICAM project. We've been using electrospinning to make some quite interesting fiber-based structures, and then integrating those with our particular material here, which is a gadolinium cerium oxide. This is a material that's catalytically active for the reactions we're interested in. So now we're talking about the reduction of steam. And then we produce these quite interesting microstructures which combine these electrospun materials with this doped cerium oxide. So this is the approach we're planning to take in the project, but we're going to not use nickel. We're going to use some titanate materials that we've been exploring in a PhD project and take that forward. If anyone's interested in looking at this sort of work, we have a paper on this for solid oxide fuel cell electrodes. And this is the result of some of our solid oxide fuel cell developments. And this so-called fiber matrix structure, at least in this study, gave us much better performance than some of the other sorts of composite electrode structures we were considering. And Dr. Huang, who did his PhD work, he will be the postdoc working on this project within bp-ICAM. So hopefully at some point we can report some, or he can report some of that work to you all. And this is the sort of microstructure we get. We're also very interested in the group in using these 3D imaging and visualization tools to try and understand microstructure and how microstructure relates to performance. And we'll be doing some of that work too in this project. So let's move on from green hydrogen from electrolysis and start to talk about some of the application areas. And let's look at the area that really has been synonymous around hydrogen for a long time, which is hydrogen fuel cells for transport. When we look at fuel cells, and this is my sort of 101 cartoon about a fuel cell, so a fuel cell is the opposite of an electrolyzer. In an electrolyzer, we put in DC power and we produce and split water to produce hydrogen and oxygen. In an electrolyzer, we're putting in oxygen, usually in the form, in a fuel cell, we're putting in oxygen. Let's talk about this type here first, which usually in the form of air. We're putting in a fuel, in this case, we're putting in hydrogen, and we're combining those together to produce water and DC power. There are two main types of fuel cells. There are other types of fuel cells available. For example, alkaline fuel cells, as a UK company, AFC Energy, are pioneering that. But here I'm going to focus on PEM and solid oxide fuel cells, so change membrane fuel cells, the low temperature type, the type that has traditionally been used in transport applications. We put in hydrogen, normally high purity hydrogen. That hydrogen is oxidized, releases electrons, forms protons. They're carried across this membrane, which has to have the characteristics of being a proton-conducting membrane. It's a polymer-based perfluorinated sulfonic acid membrane. The protons combine with oxygen from air and the electrons to produce water, and the electrons are carried around an external circuit when it's connected across a load. And that produces those flow of current, and we get a voltage generated based on the thermodynamics of the reaction. So typically about 1 volt or so when it's operating, a little bit less when it's operating at higher power, of course, because of internal losses. In the solid oxide fuel cell, which is the opposite of a solid oxide electrolyzer, we're putting in air on the one side, we're putting in hydrogen or a hydrogen-rich gas on the other. Now we're transporting oxide ions across the membrane. So this is an oxide ion conductor and forming water, but in these temperatures, steam, because these devices work at somewhere between 600 and something like 900 degrees centigrade, depending on the technology. But the overall process is the same, but we just form our reaction products on the opposite side of the device. So fuel cells are interesting because they have the highest electrical conversion efficiency of any device. A small fuel cell of 1 kilowatt in size can certainly be 60% efficient. So it's not far off the efficiency of a very large combined cycle gas turbine power plant, even though it's only 1 kilowatt in size. So really, these are an energy efficiency technology, and the carbon footprint depends on the carbon intensity of the fuel you're putting into them. So from a transport application, there's been a lot of interest for a long time in hydrogen fuel cell electric cars. This is the Toyota Mirai that we have at Imperial College, which is a hydrogen-powered Toyota Mirai. It's a dedicated fuel cell vehicle, and very nice it is to drive. It'll do you just over 300 miles on a tank of hydrogen. Of course, there is a challenge in that there are not many places to refuel it, and we can refuel it in at Gatwick, at Heathrow, at the National Physical Lab, and the M25 at Cobham and the M40 at Beaconsfield. But after that, you need to drive up to Sheffield, I think, to find the next one, though I believe Birmingham are putting in a hydrogen refueler at the moment. Or you can head west, and there's some in Wales, and there's some in Sheffield, and there's certainly some in Scotland as well. So this is where the landscape is for hydrogen fuel cell cars today. The Toyota and Hyundai would be, I think, clearly leading in terms of having products on the market. The new Hyundai Mirai is coming out this year, about £50,000, so less money with a longer range. But also the Hyundai Nexo is available, also quite an expensive car today. Hydrogen refueling is appearing, and we might discuss in chat about the relative merits of battery electric versus fuel electric. But the rule of thumb, I say, is that as you need more fuel on the vehicle, as you want to drive it further, then the merits of a hydrogen fuel cell approach start to become more clear. One area where I think there is more clarity around hydrogen fuel cell electric vehicles is in the larger vehicle market. Fuel cell electric, I think, are a really interesting application area. There's increasing interest, particularly in Asia, in hydrogen fuel cell electric to replace diesel buses. This is produced by a UK company, or the vehicles, the fuel cell subsystems by a UK company called Arcola Energy. There's also Wrightbus in Northern Ireland, or in Ireland, working on hydrogen fuel cell electric buses. If you're London-based, you can go for a ride on the RV1, which runs through Covent Garden, and they're refueled out at the Olympic Park to the east of London. And they've been carrying passengers for a number of years now on standard routes. But you can see a lot of interest in public good, high air quality, low emission hydrogen fuel cell buses around the world. I'd say a newer, but I think really interesting area for hydrogen fuel cell electric is in the truck market. As we seek to go to complete net zero economies, things like long distance trucking or heavy duty vehicles really become hard to decarbonize using batteries alone. It doesn't mean it can't be done, but it's not such an obvious place to use a battery, whereas it becomes a much more obvious place to think about a hydrogen fuel cell electric vehicle, in which you're carrying the hydrogen on the vehicle and turning it into DC power to drive all of the electric subsystems and the motors and so on. And you can see a number of programs, in fact, growing numbers of programs, including dedicated heavy-duty fuel cell products starting to be manufactured for this sort of application space. Another one that's emerged that some years ago I certainly hadn't foreseen is hydrogen fuel cell electric trains. So this is electrifying lines that are currently too expensive to consider doing overhead cables or electrifying the lines themselves, but still wanting to replace the diesel train that's on that line at the moment. And we're starting to see these now in Germany, taking passengers and performing very well. We have a prototype unit on trial in the UK at the moment that the BBC covered just a couple of weeks ago that you might have. So again, this is interesting. You go from point of use. It simplifies the hydrogen refueling infrastructure because you don't need such a widely distributed infrastructure. And it's a really interesting technology to replace diesel on lines that can't carry those large capital investments of electrification. In terms of innovation, this part of today's talk is about innovation and what new technologies are emerging. This is something in the fuel cell space I'd like to highlight. It's not my work at all. It comes from my colleagues, Anthony Kucernak at Imperial College and Dan Brett at University College. It's called Bramble Energy, and it takes a completely different approach to thinking about how you make fuel cells. And in fact, they use print technology and actually use that to produce their PEM fuel cell. The advantage of that is that you can manufacture low-cost technology using existing PCB factories. And as this is their statement that a single factory can make a 5 gigawatt of fuel cell modules per year. And of course, there are many thousands of these. And one of the challenges the sector has is how do you get to gigascale in terms of manufacturing? And this is a very interesting approach. So I'll just bring it to your attention. It came out of a Research Council funded project, and through our hydrogen and fuel cell supergen and also Innovate has been taking, and the Carbon Trust has been taking this work forward. And here are some photographs of the technology that my colleague Anthony Kucernak has kindly provided. And indeed, they raised about £5 million last summer to be able to scale this up further. I do also want to tell you about some of my own work on fuel cell commercialization in the context of fuel cell heat and power. So let's move away from transport now and dive into the stationary applications for fuel cell technology. And I start with this plot. This is from some work from our Sustainable Gas Institute looking at the natural gas consumption in households. And this plot here shows the percentage of households connected to the gas grid in different parts of the world. And that gas grid carries natural gas today. And of course, we use it for heating. The UK has the second highest penetration of natural gas into households in the world, second only to the Netherlands. Both infrastructures, of course, built off the widespread availability of North Sea gas. But you see very large penetrations in a number of other countries too. And this is a challenge because we cannot continue to burn unabated natural gas to heat our homes in a net zero energy system. We could, of course, move some of that heating load into electricity, but that in itself has some challenges, which I'm happy to discuss. For new build, I think it makes an awful lot of sense, but for retrofit, it's quite a difficult thing to do. Japan, I think, probably leads the world in thinking about some of these challenges. And this is a cartoon from Japan. It's looking at a vision of a Japanese low-carbon home in which they use fuel cell micro-combined heat and power units, this CHP micro-combined heat and power, to produce both power for the home but also heat. Coupled with renewables and coupled with some local energy storage to give you the overall low carbon footprint for that home. 300,000 customers, and probably more now actually since this slide was made, have purchased these fuel cell CHP systems in Japan. They are subsidized, but nonetheless, people still need to spend their own money on acquiring them. Now, we've been working in this area for a long time at Imperial College. And in fact, well over 20 years ago now, we had a EPSRC project. And off the back of that EPSRC project, we filed a patent. And this is the sort of front page of the patent, which was for a metal-supported solid oxide fuel cell that ran at much lower temperatures than conventional solid oxide fuel cells. In other words, they ran at somewhere between 500 and 600 degrees centigrade. This has proven to be a really interesting journey over the last 20 years. And today, this technology was taken out into a company called Ceres Power, if anyone wants to go and look at it. This is the current state of the technology. This is taken from a Ceres Power image. And this is a metal-supported solid oxide fuel cell in which we have a ferritic stainless steel foil here, coated with the ceramic layers. So if you remember the cartoon, there's an anode, an electrolyte, and a cathode. This doesn't show us the cathode, which is the air electrode, which would look like a layer of black paint over the top. Shiny surface here is the electrolyte, that's the oxygen ion conductor. In this case, it's a doped, gadolinium-doped cerium oxide. And under that is the anode, which is this porous composite of nickel and CGO that you saw in the picture about the electrospun electrodes, though these are not electrospun. These cells are interlayered with interconnect plates that join one cell to the next. And this is a photograph of an assembled stack that would be a kilowatt or so in power at that size. If anyone wants to watch the video, it's featured on the Fully Charged internet, a program that's quite good fun to watch. And this is a picture of the Horsham facility, which is not a manufacturing facility, but this is a pilot facility for cell making. A factory is being built at the moment. So this company has been very interesting. It's been a 20-year journey, and they have investors now with Bosch and Weichai. Weichai are a very large engine manufacturer in China, putting these fuel cells into buses in China. Bosch are building a factory in Germany and have the intent to put Ceres fuel cells inside of Ranger products. A deal's just been done with Doosan for example, applications in marine applications. And you can buy these in a 4.2 kilowatt CHP unit in Japan from Myra, who are one of the largest boiler manufacturers in Japan. So it's been a 20-year journey to get to this point, but really interesting, a really interesting one. So I've got just a few minutes left, and I want to talk now about energy storage. So one of the things I said at the start was the challenges of putting in more and more renewables into the system is how do you balance supply and demand? And I'm grateful to my colleague Goran Strabak, from whom I've borrowed this slide from one of his presentations. And he is a power systems engineer, and he looks at the stability and flexibility and economics of electrical systems and power systems. And he makes this point that as we put more and more wind, for example, into the UK energy system, and we need to balance supply and demand, you either have to curtail that wind more and more. This is the percentage as the wind penetration goes up in terms of the amount of installed wind turbines, and or you have to invest in infrastructure to balance that supply and demand. And you have to be able to manage these much larger peaks by putting in infrastructure, which you utilize less of the time, because the amount of energy that flows is the same, but the peak powers are much higher. And this means your asset utilization goes down, and that means the cost of that infrastructure becomes much higher. And indeed, Goran estimates that post 2030, technologies that support the flexible balancing of supply and demand are probably worth in excess of £8 billion a year. And that's the sort of ticket price you've then got to think about how you manage that. So we're very interested in my group in parts of this market, and particularly in the flow battery application. Tell you what a flow battery is at a moment. But this comes from some data from California. It's a recent report out into the impact in California of increasing PV penetration. And in California, for example, this suggests that by 2045, they're going to need something like another 44 to 55 gigawatts of 10-hour storage. So that's 440 to 550 gigawatt hours of storage in the form of 10-hour storage. And that's to balance the diurnal supply and demand coming from solar PV, just in California alone. At the moment, the market for grid-scale storage is very much more in the 1 to 2 hour market, and this is very well served with lithium-ion batteries, and I'm not planning to talk about that any further. We're very interested in this flow batteries, which are very well suited to these sorts of longer-term energy storage applications, such as 10 hours. We patented an energy storage application based on this, using a liquid gas hybrid system. There's a little cartoon of it here, and I'll show you a picture in a moment which looks at the chemistry in a little bit more detail. And it's based on the use of a liquid redox couple, and in this case, a hydrogen couple. So in a flow battery, unlike a lithium-ion battery where you're storing the energy inside your anode or cathode material in an intercalation type material, in a flow battery, you have a cell here, but much like an electrolyser, in which you create a redox couple, you create an oxidized form of that redox couple, and you create a reduced form of that redox couple. You store them in tanks, and then when you want the energy, you flow them back in together. And as a fuel cell, this then generates that electricity back. So again, along with Anthony Kucernak, who I've mentioned before in the context of Bramble Energy, Anthony and I and two of our postdoctoral team have a number of patents and created a company 2 years ago based on some novel chemistry, which we think gives us much bigger cost advantages in terms of conventional flow batteries. This is in brief the chemistry. It uses a manganese couple on the cathode side, a hydrogen in a closed loop on the anode side. And this gives us quite a high cell voltage in the context of flow batteries and a good power density. This is some data from a paper that we published a year or so ago showing extremely high power densities from this technology. And this is some recent data from the spin-out company itself, RFC Power, looking at 700 cycles and completely flat performance across 700 full discharge. This is 100% depth of discharge cycles. So we think that's interesting. And the company has 6 employees now and has just completed a seed round, which will allow us to take the work forward. And finally, well, not quite finally, but on the storage side, finally, just to point out that one of the other challenges with offshore wind is managing a period in the winter when the wind doesn't blow. We often get a period in Northern Europe when the wind is curtailed or doesn't blow in the winter, when, of course, our maximum energy demand is at its maximum. Again, I'm grateful to my colleague Goran Strabak for this slide. And it's an estimate of how much energy reserve you need in a low wind period. In this case, for thinking about hydrogen and storing hydrogen in underground tanks. And if we have a couple of weeks with low wind, we probably need 20 terawatt hours of energy storage. And that's about 2,000 pumped hydro facilities. So it's a very large amount of energy. And you can think alternatively about storing that energy as hydrogen, creating it, for example, using offshore wind, and storing it and then using it when the wind isn't blowing through underground caverns. Might sound a bit science fiction, but it's already done in the UK and in the USA and elsewhere for completely different reasons. So we know technologically it's a valid approach. And indeed, there was a recent nice article on this, looking at the potential of salt caverns for hydrogen storage in Europe. And if we think we need 20 terawatt hours, that's about here on this plot. And this is looking at the capacity across a whole range of different European countries. And we can see that all of these countries have the capacity to balance that seasonal energy demand with hydrogen underground storage if they wished. And finally, and it will be finally because I'm out of time, we mustn't forget that we make hydrogen today. We make hydrogen today for the chemical sector. We make it as a feedstock. 96% of that hydrogen is made from fossil fuels today. It's made from natural gas and coal. 6% of the world's natural gas is used to make hydrogen, and its use goes into things like ammonia and petrochemicals. If we look at where projects are today about green hydrogen, there are really interesting projects around displacing brown hydrogen. That's hydrogen from fossil, hydrogen from coal and gas, with green hydrogen. I just highlight three. This project with Shell in Rotterdam, which has been announced to make 50 to 60,000 kilograms of green hydrogen per day. The largest green hydrogen project in Saudi Arabia to make green hydrogen and green ammonia and export that into international markets. That uses an alkaline electrolyzer. And then BP's own project, which was announced late last year with Ørsted, using offshore wind and coupling that with BP's Lingen refinery to help decarbonize that refinery business. So I'll stop there. I hope what I've shown you is that electrochemical technologies are flexible. They offer high efficiency. In a world in which we're liking to decarbonize, I think they're going to be increasingly important. Materials matter, as does device manufacturing. And so I think that's something for all of us working in this space to recognize. I think we have a great science base in this field. And as I say, we've just started, as well as a very interesting industry base. And we've just started a project with bp-ICAM, which we look forward to sharing. Subsequently, if you are interested and want to look in any more detail at our own work at Imperial, the Hydrogen Fuel Cells Hub, the Sustainable Gas Institute, or indeed the broader energy program at Imperial, please do look at the websites.